Hello, everyone. So thanks for being here. I had to swing by my office to grab a couple things and forgot the pen to my Wacom tablet. So it is currently useless for me. So we're going to go over the guided notes that are already filled in. I won't be able to do a whole lot of example problems. We're in a good place anyway, though, for lecture. So I don't think we will be lecturing the whole time anyway. So we'll kind of just do a little bit of an overview today. Okie-dokie. Okay, so the last chapter of this class really is chapter 13. And it's all on solutions. And so if we go back to the very beginning of the class when we were trying to define matter as being a compound or an element or a mixture, solutions are going to be a type of mixture, specifically a homogeneous mixture. Sometimes we go with the word homogeneous mixture, meaning it's a mixture of two or more substances that are even throughout, or they're the same throughout. So salt water would be an example of a homogeneous mixture. Evenly mixed, if I was to take a sample from the top, or a sample from the bottom, or a sample from, a really large container or a small container, we would expect it to have a similar concentration and composition, versus a heterogeneous mixture, which is a mixture that isn't the same throughout. So bananas and oatmeal, right? Some bites are going to have more bananas, some will have more oatmeal. So when we're looking at a homogeneous mixture or a solution, we will have two parts. The minority component is called the solute. So that's what's getting dissolved. And then the majority compound, or what's doing the dissolving, is known as the solvent. And your solute plus your solvent equals your solution. Now, there can be solutions that have more than one solute, more than one thing that's being dissolved in them. For the most part, though, what we're going to be looking at will just be one solute, one solvent, like salt with water. The water would be the solvent, the salt would be the solute. It's not always the case that the minority is the solute. Sometimes the minority actually is the solvent, but because it's doing the dissolving, like for instance, water, we would always classify that as the solvent. Over here, we have a can of Coke, which is a good example of a solution that has a couple different things in it. So the solvent is water. So most of what a can of pop is just H2O. Then we have CO2 in it, which is actually a gas, a dissolved gas. That's what gives it that effervescent quality to it, or the fizzy quality. We have dissolved sugar, and sugar being normally a solid. And then we also have corn syrup, which is a liquid. And if you notice, all of these are in different phases, gas, solid, and liquid. But when they're dissolved in your solvent, they become the same phase as the solvent, right? So the whole pop itself is a liquid. So this whole thing is a liquid, even if these on their own are different phases. So we kind of already have talked about this idea of likes dissolve likes, but if we could separate materials into being either polar or non-polar, polar things will be dissolved by polar solvents, non-polar dissolved by non-polar solvents. And whether something is polar or not is when it has that dipole moment or there's some sort of asymmetry in the structure. So water is a really, really good example of a polar material. If I was to draw out the Lewis dot structure of that, we've got oxygen with two hydrogens, and then we have two lone pairs of electrons on that oxygen atom. So the oxygens in general have an overall negative dipole. The hydrogens have an overall positive dipole. And we can also think of it as like hydrogen bonding from the last chapter. And what this water will do is it will pull on anything that also has a polar component to it. So this molecule right here, methanol, it's going to be carbon with 3 hydrogens and then 1 OH group popped off of it. This is what gives it that polar quality. So these two would definitely dissolve in each other. They're both polar and they have hydrogen bonding. Here we've got NaCl and H2O. H2O polar solvent, NaCl, also an ion. So we get this dipole attraction, or the positive hydrogen side will sort of pull on the negative chlorine, and the negative oxygen will go ahead and tug on the positive sodium. And that attraction between solvent and solute is greater than the attraction between the Na and the Cl. So we'll get it to dissolve. Here, this last one is where we have a situation where we've got water, which is H2O polar, mixing with a non-polar material. So here we've got just a simple hydrocarbon, 3 carbons with hydrogens all around it. The structure is very, very balanced. We don't have any OHs off of it. So we would say that this is a non-polar material. This will not dissolve in our water. So certain substances will dissociate when we put them in water. NaCl is an example of that. The substance goes ahead and breaks apart into its ions whenever it's put into water. And depending on how far it breaks apart, we can classify it as being strong or weak or doesn't dissociate at all. So anything that's considered a strong electrolyte solution, HCl, NaCl, so strong acids or certain salts, will have a complete dissociation. And one way that you can read this off of a formula, or rather an equation here, is I have HCl, and if I put it in water, we have a single arrow. And the single arrow means that this molecule will completely break apart into hydrogens and chlorines. So you're gonna get a lot of bang for your buck. Here are all the strong acids that we have. So hydrochloric acid, hydrobromic acid, hydroiodic acid. We've got chloric, well, here's chloric acid and chlorous acid. We've got nitric acid and sulfuric acid. So you will want to have those memorized, or you want to have access to those. Anything else outside of these will be considered a weak acid. Another type of strong, again, are going to be your ionic compounds. So metals combined with either nonmetals or polyatomic ions. So these two groups are going to give us an arrow moving in one direction. We know that if we drop these things in water, we're going to expect to have lots and lots of ions. We can also have something called a weak electrolyte solution. So it's still an electrolyte solution, but you're not getting quite as much bang for your buck as far as how many ions you get. So partial dissociation is happening. Usually they classify that as around 5%. We've got hydrofluoric acid. So really any of the acids, again, that are not these are considered our weak acids. So HF will break apart into its ions, H plus and F minus, but there also will be a certain percentage of recombination. So the H and the Fs will come back together to form the molecule. When we have it in this form over here, the charges are neutralizing each other, so we don't have any sort of electrolyte properties. It's only when we break them apart into these ions that we get the electrolyte property of being able to conduct electricity and things like that. The double arrow is a good indicator, okay? So that's just letting you know, hey, we are dissociating, and then we are also doing this thing called recombining. Here are some other ones that will, so we've got HCN and HC2H3O2. Sorry, hold on 1 second. There was apparently a kid got shot. They're okay, but a kid got shot at Hendersonville Middle School. And my really good friend works there with her daughters. So I'm getting like all these text messages. It looks like everybody's good, but there is a girl in the hospital. Okay, chemistry. So strong electrolyte solutions, we get that complete dissociation. Weak electrolytes, we get a partial dissociation. And then at the very bottom of this, or the third one, we have what's known as a non-electrolyte solution. So we have something that is dissolving, but it's not breaking apart when it dissolves. So it's not breaking apart into like an H plus and a Cl minus where we get these ions. In this case, we're just changing the phase. So here I've got C6H12O6 and it's in liquid form, and I mix it with water. It stays in this molecular form, but it's just changing its phase. So it's going from a liquid to now being aqueous or dissolved. This is what sugar does. So sugar is a non-electrolyte solution. Yes, the sugar will dissolve in the water, but the sugar is not breaking apart into individual carbons, hydrogens, and oxygens. So if we were to apply these to a couple different things, which you're going to want to be able to do, classifying them as a strong electrolyte, a weak electrolyte, or a non-electrolyte solution. We can see here CaCl, this is ionic, so we're going to say that's a strong electrolyte solution. The HNO3, that's a strong acid, so that also is going to be one of our strong electrolyte solutions. Anything that contains non-metals like this, these are not going to break apart into ions, okay? In order to get some sort of ion or charged particle, you either need to be an acid or you need to be some sort of ionic compound. So anything that looks like this, where we've got a molecular compound or non-metal, non-metal, and non-metals, we're going to say that's a non-electrolyte solution. In those cases, we're just changing phases. So we take the liquid ethanol and turn it into aqueous ethanol. The HCHO2, so this is formic acid. This is a weak acid. How would you know it's a weak acid? You would just reference this here and say, well, it is not any of those. So I'm going to go with it being a weak acid. Weak acids will give us a weak electrolyte solution. And then KOH, anytime you've got that metal and that non-metal, you've got that ionic situation, we're going to say that that is a strong electrolyte solution. So how we can relate this sort of to numbers, if we consider the following solutions. So we have 1 mole of each of the following, and we're going to dissolve them in 1 liter of water. So I've got 1 mole of CaNO3, or calcium nitrate. We've got 1 mole of glucose, C6H12O6, and then we've got 1 mole of this NaC2H3O2, which is sodium acetate. And we also have acetic acid, okay? So same compound on the second component here, but we have an H. Rank the solutions in order of increasing electrical conductivity based on the fact that the greater the number of ions in solution, the greater the conductivity. So the more ions you can get, the easier it's going to be to have an electrical current. So obviously if you have no ions, you're not going to conduct anything. So of these, right here in glucose, I can see that there are no metals in there. It's all non-metals. So right off the bat, I know that's a molecular structure. That is not going to conduct any sort of electricity. So right here, we've got the glucose. We're going to say molecular, and there are no electrolytes. So that's going to be the lowest. From there, I can see over here that I have acetic acid, and acetic acid is not one of the, if we go back up here, it's not one of my strong acids. So if it's not a strong acid, it has to be a weak acid. If it's a weak acid, we know it's also going to produce a weak amount of electrolytes. So we've got weak electrolytes here. So this guy is going to be slightly stronger than this one, or give us a little bit more current. This is no electrical current. This is a little electrical current. From there, I've got two ionic compounds. I've got CaNO3 and then NaC2H3O2. So when determining which one of these, they're both ionic, so they're both strong electrolytes. We want to figure out which one's going to be better at conducting electricity. You've got to count up how many ions you're going to get if you were to break them apart. And the thing that gives you more ions is going to be the thing that conducts electricity better. So looking at this here, I've got one sodium and then I've got one acetate ion. So I'm going to clump this whole thing together, right? This will break apart in like a polyatomic ion. We'll keep that thing as a unit. So in this, I've got one ion here and then one ion here for a total of 2 ions. So I expect every single one of these molecules to break apart and we would get 2 ions. This guy here is a little bit more effective. I have 2 calciums, and then this is a nitrate. So we keep the nitrate together, but notice I have 2 nitrates. So every time I break this molecule up, I'm going to get a calcium and 2 nitrates, or a total of 3 ions. 3 ions is going to be more effective at electrical conductivity than 2 ions. So then just simple ordering those up, the lowest will be the glucose because we don't have any ions. Next will be the weak acid. Then we'll go to our ionic structure that has only 2 ions, and then our ionic structure that has 3 ions. If we had something else that had 4, 5, or 6 ions, right, we would just continue to stack those on top of each other. Give me just a second. Okay. So when we're talking about a compound, like let's say we are talking just about sodium acetate, that has a very specific ratio, right? I've got 1 sodium for every 1 acetate. It's sort of, the formula has this very rigid built-in composition. It's different with solutions because a solution is a mixture, so we can have more or less of one or another thing. I can have a really salty water solution or a very, very dilute solution. And so, whereas with compounds, you only have one recipe. Solutions, you can have multiple recipes. You can have something that's really, really chocolatey or not quite so chocolatey. So as far as how we classify different types of solutions, saturated solution is a solution that contains the maximum amount of solute for that given solvent. And that is temperature dependent. So for instance, at 25 degrees Celsius, 100 grams of water can hold 36 grams of salt. If it had exactly 36 grams, we would say it is fully saturated. An unsaturated solution, so there's really only going to be one saturated point at a given temperature. An unsaturated solution contains just anything less than the maximum amount. So there's quite a few different options for an unsaturated solution. So again, if Saturation is 36 grams at 100 grams of water. An unsaturated solution could be 35 grams of salt in 100 grams of water. It could be 32.664. It could be 1, right? Anything where you have a little bit more room or a lot more room to pack more salt or material in. We do have these unique situations where we can have what's called a supersaturated solution. So this solution contains more than the maximum amount of solute at a given temperature. This is a very unstable situation. You can form one of these by heating up the solution. Hot or warmer temperatures solvents will hold more solid. So if I took a salt water, heated it up, I could actually pack more salt in, and then very slowly I would cool it back down. And if I did that really, really slowly, I could create sort of this unique situation where it will hold on to the salt. But it's unstable, and if I was to throw, even a single drop of salt in that supersaturated solution, a lot of the excess salt would end up precipitating out. So looking at different factors that affect solubility. So our intermolecular forces between the solute and the solvent particles have an effect. So likes tend to dissolve likes. So if we're looking at this here, predict whether each of the following substances is more likely to dissolve in carbon tetrachloride, which is CCl4, or in water. So the difference between these two things is that carbon tetrachloride is a non-polar material. So we would have carbon in the center and 4 chlorines surrounding it, nice and balanced. There wouldn't be any lone pairs. Water is always going to be our go-to polar solvent. So we've got these items here, and we want to decide whether they're going to dissolve in something non-polar or polar. Well, looking here, this thing, I know right off the bat, this is definitely non-polar. 2 iodines bonded to each other. This guy over here is also non-polar, 7 carbons surrounded by 16 hydrogens. So the non-polar things are going to dissolve with the non-polar solvent. Na2SO4, all the ionic stuff, ionic is always going to be polar. And then HCl is also a polar material. The acids will be polar and the bases will be polar. Those will dissolve in water. So you'll want to be able to pick out polar versus non-polar molecules and classify then if they'll dissolve in something polar or non-polar. I think that the toughest part is being able to look at it and decide, is that polar or non-polar? So getting comfortable with it, something that looks very balanced versus something that has that imbalance to it. If on this structure, it was C7H15 and then there was an OH to it, like we had, where were you? Up here, this creates that imbalance quality to it. So pressure does, in some instances, have an effect on solubility. It doesn't affect if we have a solid or a liquid dissolved in a liquid material. But the solubility of gases will increase with increased pressure. This is known as Henry's law. So if we increase the pressure above the liquid, we can increase the amount of gas that's dissolved. And our go-to example for that would be a closed can of pop versus an open can of pop. So in a closed can of pop, it's sealed off, it's pressurized. The airspace that sits above the liquid, let's not even think of a can, let's think of a glass bottle, okay? So we've got that closed off and we can see inside of the glass bottle. So what you'll find is that the head space that sits right above the liquid is pressurized. And so you don't see any bubbles coming out of solution in your closed bottle of Coke. But when you open that can, what happens is you depressurize the head that sits above the liquid, and all of a sudden now bubbles start to come out of solution, or it starts to fizz. Why is it fizzing when you open it? Because you don't have as much pressure, so you're decreasing the pressure, which means that you're decreasing the gas's solubility.
Can you say what, under factors affecting solubility, subscript A, what does IMF stand for?
Intermolecular force. Your intermolecular forces from the last chapter. So there's actually an equation that you can use for this Henry's law, for this relationship between pressure and the solubility of gas. It's really simple, but it says the solubility of the gas, and that's our SG, is equal to K, which is Henry's law constant for that gas in the solvent. So there's a specific thing for that, for whatever the given problem is. And then PG is the partial pressure of the gas that's sitting above that liquid. So, you know, just two variables and a constant that you could get out of an appendix. So if we calculate the concentration here, it says calculate the concentration of CO2 in a soft drink that is bottled with a partial pressure of CO2 of 4.0 atms over the liquid at 25 degrees Celsius. The temperature is important. The Henry's law constant for CO2 in water at this specific temperature is 3.1 times 10 to the negative 2 moles per liter ATM. So we're trying to figure out this SG, or the solubility of the gas. We know our constant here, which is given to us, or you would reference it from some appendix. And then we also know the pressure of that gas. So the CO2 partial pressure that's sitting above is 4 atm. So when we put this into our equation, our units are kind of funky, right? We've got mole per liter ATM here. We multiply it by a pressure or an ATM value. Our ATMs will cancel out. We end up getting a value of 0.124 moles per liter. So what that's telling us is that for this specific gas, which is CO2, we would expect to find in a given liter of that pop, 0.124 moles of the gas. If the pressure, so if this number here increased, let's say instead of it being 4 atms of pressure, it was 8 atms of pressure, then our overall amount would actually double, right? We would have 0.248 moles in every liter. And then the same is true for if we were to decrease our pressure. So if this is a closed can of pop and we were to open it up and drop that 4 atms down to, let's say, 1 atm, because now we're at sea level and the gas escapes, we would expect our moles per liter to also be cut down by a factor of 4. How is that going to happen? The gas is going to leave the liquid, so it will form bubbles and it'll escape as well. Temperature, so again, pressure affects our solid, it doesn't affect our solids and liquids, it only really affects our dissolved gases. Temperature, on the other hand, will affect a couple different things in a couple different ways. So in general, when we're looking at the solubility of solids dissolved in a liquid, as the temperature increases, the solubility of the solid will also increase. So an example of a solid could be salt, or maybe you'd be more comfortable with sugar. It's much easier to dissolve sugar in warm tea than it is cold tea, right? If you're making a simple syrup for lemonade or something like that, you heat the water up to dissolve the sugar. So higher temp, higher solubility for our solids. But the opposite is actually true if we're talking about dissolving gases in a liquid. As the temperature increases for the solution, the solubility of the gas will decrease. So we could, an example here, CO2 gas. So how do we tend to have our pop or our beer served? We usually like to have it served cold. Why? Because it keeps the drink fizzy for longer. It keeps it more effervescent. If you have a warm can of pop or a warm beer, you will notice that it goes flat really, really quickly. And it's because the liquid can't hold on to the gas. The gas can't stay dissolved. So warmer temperature, less solubility of gases. Colder temperature, we're going to keep that fizz, or we're going to keep the gas longer in solution. And so, like I said before, with formulas, like for instance, CO2, we have a carbon and it's mixed with 2 oxygens. That's what makes CO2 CO2. With solutions or homogeneous mixtures, it's important to let the reader know how concentrated that solution is. And there's a bunch of different ways that we can express concentration, or how much solute do you have in relationship to the solution. The first way is mass percent, which shouldn't feel too foreign. We've kind of already gone over something pretty similar to this. A lot of times it's written like this: M with a divisor bar, M percent, mass percent. And this is the solution. So it's going to be grams of solute over grams of solution. And I want times 100 because it's in a percentage. For this denominator here, make a note somewhere that says, you know, in parentheses, you can write, I wish I could write on something, but I can't, solute plus solvent, okay? This is both the solute and the solvent. What happens sometimes I see with people using these equations is they'll go grams of solute divided by grams of solvent, or like grams of the salt divided by grams of the water. But you actually have to include the grams of the solute on the bottom denominator as well. It's part divided by total. So here's a good example of that. What is the mass percent, or sometimes it'll say mass percent, of sodium hydroxide in a solution that is made by dissolving, we have 8 grams of the NaOH in 50 milliliters of water. And it says, hey, FYI, the density of water is 1 gram per milliliter. So if we know the milliliters, it's really easy to get the grams, right? 50 milliliters of water is the same thing as 50 grams of water. So if I want to calculate the mass percent, what I don't want you to do is take 8 and divide it by 50, because you would be taking the solute and just dividing it by the mass of the solvent, when in reality, we want the bottom component to be the full solution. So we need to be taking our solute, adding it to our solvent, or the salt plus the water, which would give us a total of 58 grams. That's why that number 58 is down there. So 8 grams divided by the 58 times 100. And in this case, it would be 13.8%. If you didn't add the 8 down here, you would be overcompensating for how much salt there actually is in solution. So let's see how I can do this. I'm going to give you a problem. I'm going to type it up. Let's see how it works.